Hello, this is example 3 from section 4.5 on optimization problems. And this problem is geometry related. So here we're asked, what are the dimensions of the rectangle of largest area that can be inscribed in the ellipse x squared plus 4y squared equals 16 that's shown below? So first things first here, would be good to know what this word inscribed means. That way we know what we're doing. And basically, inscribed is just a synonym for drawn inside of something. So what's the dimensions of the rectangle of largest area that can be drawn inside of the ellipse that's in this picture? And this ellipse, by the way, if it's been a little while since you've studied your ellipses and conic sections, you'll notice that the ellipse here stretches out to the points 4, 0, and negative 4, 0 along the x direction. Then in the y direction, it goes up to 0, 2, and then the lowest it goes is 0, negative 2. Okay, so that's kind of the boundaries of our ellipse there. And we are looking for the rectangle of largest area that can be drawn inside of this ellipse. And to really, maximize our space here, we don't want to just draw like a little tiny rectangle in the middle of the ellipse somewhere. No, we want to make it as large as possible. So we want to stretch that ellipse or stretch that rectangle out until it touches the edges of the ellipse. Now, there's still a variety of different rectangles that could do that. For instance, you might have a rectangle that looks like this. Okay, there would be one version. All right, you might have a rectangle that's tall and skinny like this. That one looked like it went outside the ellipse a little bit. That's just my drawing skills. It's still inscribed inside of the ellipse. There we go. And we can see between just those two samples I've drawn, one of those clearly has a larger area than the other. This horizontally oriented rectangle definitely has more area inside of it than this little vertical rectangle does. So our options clearly have different areas to them. Now, those are just two examples. You could have something in between that, maybe a rectangle that looks something like this. Okay, there are a ton of different possibilities for what we could do with this. Okay, so there's kind of some sample pictures. Let's stick with just one of those to kind of base our sketch and our variables off of. I think I'll go with kind of that middle selection here. Okay, so I'm going to get rid of the more extreme rectangles and put that one in a bit more solid. Okay. Remember, this is just a sample. It doesn't necessarily look like my sketch, so don't assume like the size of certain values based on the picture here. All right. And because of that, because we don't really know what the size of this rectangle is, we better put some variable labels on this and quick. All right. So I'm going to label this in hopefully a way that's going to help us with the setup of this problem. And my labels are going to be based off of the fact that we have a point that's on the ellipse here that makes a corner of the rectangle in the first quadrant. We're just going to call that X, Y. Okay, because that then gives us good information to work off of. Okay, it tells us that this distance right here is Y, and that this distance right here is X. Okay, So that is then going to give us, in turn, information about the full rectangle. If we were to look at the full height of this rectangle, it's nice and symmetrical. Okay. So this height is just going to be 2y. And then real similarly, with the width of the rectangle, going across this dimension here, that's just going to be 2x because these portions are symmetrical. That's what we get from centering the rectangle in the middle of the ellipse like this. So 2x there. Okay, so we've got a sketch and we've got it labeled. Now let's state our goal here. Okay, so the goal is to find the dimensions of the rectangle of largest area. And those are our keys to the goal right here. Largest implies that we are maximizing. And what are we maximizing? The area. So goal is to maximize the area of the rectangle. Okay. So we need to come up with an equation here for the area of this rectangle. Doing an equation for our quantity of interest. Okay, and here, area of a rectangle is just length times width. All right, which I'll put LW for right now, but based on our sketch, we can see that our length of the rectangle, length or height would be 2y, and the width would be 2x. Okay, so it's 2y by 2x. Okay, and so we are going to have an area equation of 4xy. All right. Now, as we have seen in these optimization problems, this is pretty standard at this point. We have an equation, but we can't quite use it yet to find the maximum because in this form with two different variables in there, x and y, we can't really take a really useful first derivative of this. So we're going to need to get this equation in terms of just one variable. And so let's see how we would do that. All right. So what is our other bit of given information that we haven't quite used yet here? Okay, we've got a rectangle of largest area inscribed in the ellipse. There's a nice big equation right here that we have not used at all. And that's what we're going to need to use for our given information here. Okay, so this is our given information. This is the constraint equation for our optimization problem. So the constraint is that our point xy should actually lie on that ellipse. So it lies on the ellipse. Okay, and that's necessary to make this rectangle as large as possible. So xy, our point coordinates, need to satisfy the ellipse equation. X squared plus 4y squared equals 16. All right. And so we are going to need to solve that for one variable or the other. And let's see, you can go either way with this. It should work out fine either way. I'm going to solve for x because it looks a little bit easier to me. Okay, so x squared equals 16 minus 4y squared. And then to square root both sides of that. Okay, technically we would have x equals plus or minus square root of 16 minus 4y squared. But notice how our point that we've labeled here, the xy, is in quadrant 1. And so the way that we've set this up, the way that we've labeled it, will allow us to choose the positive square root for that x. Okay, so x in quadrant 1 can use positive root. Okay, so x would be the positive square root of 16 minus 4 squared. Now remember, one thing to be very careful about there, notice that that is not 4 minus 2y, okay? You cannot split a radical over addition or subtraction. It's something that's so tempting for people, but don't do it. Doesn't work that way. All right, but there is something that we can do here, which is to factor out a perfect square. Inside of both of those terms, there is a 4, so we could take that and split our radical, square root of 4, and then the square root of 4 minus y squared. And so that's actually an okay operation here. You could say that x is going to be 2 times the square root of 4 minus y squared.